Hello again, and welcome to Quantum on the Treadmill. In case you hadn't noticed, this series is an experiment for me to learn how to use AI to create new audio and video content effectively. From time to time, I will switch between different tools to see which ones are more cost effective and which ones deliver better quality. Today's video is an example of better cost but lower quality. I hope you still enjoy it. As Bohr, the bridge between Planck and Schrödinger. When people tell the history of quantum mechanics, they often jump from Max Planck to Erwin Schrödinger, stopping briefly to mention Niels Bohr along the way. That does Bohr a disservice. Planck discovered the quantum, Schrödinger explained it, but Bohr built the bridge that connected the two. By 1900, Planck had resolved the ultraviolet catastrophe with an idea he initially regarded as little more than a mathematical device. He proposed that energy could only be exchanged in discrete packets proportional to the frequency of light. His deceptively simple equation, E equals hf, changed physics forever. Frequency was no longer merely a property of a wave, it determined the smallest possible unit of energy that light could carry. Planck himself remained cautious. He did not yet believe that nature was fundamentally quantized. Yet his equation matched observation with astonishing precision. For more than a decade, however, the quantum remained homeless. It explained radiation, but not matter. It told physicists something profound about light while leaving the atom largely untouched. That changed in 1913. Bohr looked at Rutherford's newly proposed nuclear atom and immediately saw a problem. According to classical electrodynamics, an electron orbiting a nucleus should continuously radiate energy, spiral inward, and collapse into the nucleus almost instantly. Stable atoms, and therefore chemistry, biology, and ourselves, should not exist. Rather than modifying Maxwell's equations, Bohr asked a far more radical question. What if the electron itself was restricted? His answer was breathtakingly simple. Electrons were allowed to occupy only certain discrete energy levels. They could not exist between them. An atom was not free to possess any energy. Nature permitted only specific values. Then Bohr performed the conceptual move that transformed Planck's idea from an isolated insight into the foundation of atomic physics. When an electron moved from one allowed energy level to another, the difference in energy was emitted or absorbed as light, not just any light. A photon whose energy satisfied Planck's equation, delta E equals hf. This was the missing link. Planck had discovered that light comes in discrete packets. Bohr proposed that atoms themselves possess discrete energies. The two ideas suddenly fit together. Light and matter were no longer separate mysteries. They became two sides of the same quantum story. Yet Bohr's model still carried one foot in the classical world. His electrons were pictured as tiny planets orbiting a miniature sun. Those orbits were quantized, but they were still orbits. Schrödinger would eventually reveal that this picture was only an approximation. In 1926, he replaced Bohr's circular trajectories with wave functions. Electrons were no longer tiny particles tracing paths through space. They became standing waves surrounding the nucleus. The familiar orbits survived only as discrete energy states arising from stable wave patterns. Seen from this perspective, Schrödinger did not overthrow Bohr. He explained why Bohr's energy levels existed in the first place. The progression is remarkably elegant. Planck quantized the oscillations of electromagnetic radiation. Bohr quantized the allowed energies of the atom. Schrödinger showed that those energies arise because matter itself behaves as a wave. The history of quantum mechanics is often presented as a series of disconnected breakthroughs. I see something different. Each physicist solved the problem the previous one left behind. Planck answered why light comes in discrete amounts. Bohr answered why atoms are stable and why they emit discrete colors. Schrödinger answered why Bohr's quantized atom works at all. Without Planck, there is no quantum. Without Bohr, Planck's quantum theory never enters the atom. Without Schrödinger, Bohr's atom remains an inspired but incomplete model. That is why Bohr deserves to be remembered not merely as one of quantum mechanics' pioneers, but as its indispensable bridge. He carried the quantum from radiation into matter and opened the path to the wave mechanics that defines modern physics.